In the last video, we talked about the idea of splitting apart a complicated rational function into more simple partial fractions so that we could integrate. We looked at the idea of the decomposition and what the form would look like for these examples. And for this video, we want to solve some complete integral problems from start to finish, where we're trying to split apart the rational function using partial fraction decomposition and then integrate. Let's take a look at our steps. Our first step is to factor the denominator. Then we rewrite the fraction in the partial fraction form. And the next step is to solve for the associated constants. Once we've done that, then we want to integrate. And let's just note that sometimes, with these particular problems, when we have partial fractions with irreducible quadratic factors, we might need to use a special identity for integrals of this form. So when we have an integral of 1 divided by x squared plus a squared, this has the antiderivative of 1 over a times the arctangent of x over a. We'll see some examples of this form, and we'll see how to use that particular identity. We could actually prove this using integration by substitution, but we don't need to worry about that. We'll just see how to use it. In general, for some of these examples, it would be necessary to complete the square. We will not see any examples of this type, but to solve a generic rational function, that may be necessary. Let's take a look at example 3. We want to solve the integral of 5x plus 1 divided by x squared minus 1. We first double check that the degree of the denominator is greater than the degree of the numerator. It is, so we do not have to do long division. And the next step is to factor the denominator. So I'm just going to take out the rational function and factor the denominator. X squared minus 1 is the difference of two perfect squares. So this factors as x minus 1 times x plus 1. Once I have fully factored the denominator, I want to write the form of the decomposition. Each of the factors gives me a new fraction. And because these are both linears, I have a single constant for both of them. My next step is to solve for these constants a and b. To solve for these constants a and b, I need to multiply both sides of this equation by the denominator, x minus 1 times x plus 1. When I do that, I have cancellation on the left, and I'm just left with 5x plus 1. On the other side, I need to distribute to both of these terms. When I distribute to the a, the x minus 1 factors cancel, and I will have a times x plus 1. When I distribute to the b fraction, the x plus 1 factors cancel, and I will have b times x minus 1. Now I want to expand this out and try to group like terms. Ax plus a plus bx minus b. Now I want to group terms according to multiples of x. I have an ax and a bx, so I group those together. And then I have two constants, a minus b. I can factor out an x in these first couple of terms, and I have a plus b times x plus a minus b. This equals 5x plus 1. I'm trying to solve for a and b, and I have a polynomial on one side equal to a polynomial on the other side. Two polynomials are equal if all of the corresponding coefficients for the same degree terms are equal. In other words, the 5x has to equal the a plus bx, and this 1 has to equal a minus b. So this gives me two equations for a and b. The first one, a plus b equals 5. The second one, a minus b equals 1. And now I solve for a and b. From the second equation, I can write a as 1 plus b. And if I substitute that into the first equation, a I substitute with 1 plus b equals 5. So 2 times b equals 4, b equals 2. If b equals 2, I take that value for b plug it into this expression for a, and I obtain a equals 1 plus 2, a equals 3. A equals 3, b equals 2. I will put those constant values into the decomposition form. So I can rewrite my integral as the integral of a over x minus 1, but a is 3, so 3 over x minus 1, plus b, 2, over x plus 1 dx. I have found the appropriate constants a and b so that I can decompose the original rational function into these two partial fractions. Once I have decomposed the original rational function, I can now integrate each of these fractions separately. The antiderivative of the first is 3 times the natural log absolute value x minus 1. The antiderivative of the second is 2 times the natural log absolute value x plus 1, add plus c, and that is our final answer. Notice that the majority of the work for this problem was doing the partial fraction decomposition. Once we successfully decomposed the fraction into smaller fractions, it was relatively easy to find antiderivatives. Let's take a look at example 4. Once again, the first step is to factor the denominator. So we look at our denominator and see if there's a way that we can factor it. This one's maybe a little bit trickier, so we might want to use the quadratic formula to find the roots of this quadratic. But this factors as 2x minus 1 times x plus 3. If we were to FOIL that out, we would have 2x times x is x squared, minus x plus 6x is the plus 5x, minus 1 times 3 plus 3. That is the correct factorization. Once we have the factorization, we want to write the form of the partial fraction decomposition. So I'll just write my rational function here. I have two linear factors. So I will have two fractions in the decomposition. I'll have a constant a over 2x minus 1, constant b over x plus 3. In order to solve, I multiply both sides of this equation by the denominator, 2x minus 1 times x plus 3. On this side, the denominators cancel. I'm left with 14x plus 7. On the other side, I need to distribute the denominator to both of those fractions. Once again, when I distribute to the first fraction, the 2x minus 1s will cancel, and I will have a times x plus 3. When I distribute to the second fraction, the x plus 3's cancel, and I have b times 2x minus 1. Now I distribute and group like terms. ax plus 3a plus 2bx minus b. I want to group the x terms together. Notice that when I group the x terms together, I have an a and a 2b. So I'll go ahead and write this as a plus 2b, all of that times x. And then I have these constant terms left, 3a minus b. This equals 14x plus 7. Once again, in order for two polynomials to be equal, the corresponding coefficients have to be the same. So 14 must equal a plus 2b, because it's the coefficient on the x for both sides of the equation. The two constant terms also must be equal. So 7 must be equal to 3a minus b. Now I need to solve for a and b. I think the easiest way to do that here is to solve the first equation for a. We have a equals 14 minus 2b. Then in the second equation, we replace the a with 14 minus 2b. So we have 7 equals 3 times 14 minus 2b minus b. We expand, group like terms, and solve for b. 3 times 14 is 42, minus 6b minus b. Subtract 42 from both sides. I have a negative 35, which is equal to negative 7b. Solve for b, and we have b equals 5. Once we have the value for b, we know that a equals 14 minus 2b. So a is 14 minus 2 times 5, which is 10. A equals 14 minus 10, which is 4. So we have a equals 4, b equals 5. All right, now that we have those values, that gives us the partial fraction decomposition for our expression. Let's make a little bit more space here, and then we'll solve the integral the rest of the way. All right, so our integral becomes the integral of 4 over 2x minus 1 plus 5 over x plus 3. Notice that so far in this problem, we have not done any calculus. All of the work that we've done has been an algebraic technique called partial fraction decomposition, and the whole point was to take this complicated rational function and split it apart so that we can now integrate. So integrating the first fraction, this is a natural log. We have 4 times the natural log of the absolute value of 2x minus 1, and we have to compensate by dividing by 2 because of the 2x inside the natural log. For the second fraction, this is 5 times the natural log absolute value of x plus 3. We add a plus c, and that is the correct antiderivative.